We shall move on to the next lecture on advanced level problems on fluid statics, lecture number 4 in the series. And you remember in the last lecture, that is number 3, we started problems based on variation of pressure in a liquid or fluid rather in an accelerated vessel. But so far we only considered cases where the vessel is given a horizontal acceleration or a vertical acceleration or an acceleration up an inclined plane. Now in this lecture we shall be starting with problems where the vessel is made to rotate about an axis so that every particle of liquid possesses a centripetal acceleration. We shall consider many varieties of problems on this topic, and only if time permits we'll go for some other types of problems. And as usual we shall mark the problems with dots. 1 dot means problems relatively simple, 2 dots mean problems of moderate difficulty, and 3 dots mean challenging problems. So let us start with the problems going to a fresh page. Now for numerical calculation, I shall make use of equation number 3 here, although either of the result is perfectly all right. And let us write down the data given in the problem, that is R0, radius of this space station, that was given to be 55.0 meter. Also, Kelvin temperature of the station was given to be 295 Kelvin. These two taken from the question. When you also require the free fall acceleration on the Earth's surface, G is equal to 9.80 meter per second square. M0, that is the molar mass of air, and assuming that air is a mixture of about 78% nitrogen, 21% oxygen and 1% argon plus carbon dioxide, the average molar mass of air, that's a mixture of gases, can be shown to be about 29.0 gram per mole, that is 29.0 into 10 to the power minus 3 kg per mole. You remember this is a fundamental unit in SI of amount of substance. The whole word is MOLE, mole, but MOL is abbreviation for that, and that is the molar mass of air, which is a mixture of a number of gases. So, and capital R, that is the universal gas constant appearing in the equation of state, its value is 8.31 joule per mole per Kelvin. When I put these values here, that is within square brackets, you can show that minus half into M0 into G into R0 by capital R into T, this will come to be minus 3.188 into 10 to the power minus 3. A number only without any dimensions, and this is in 4 significant figures. Therefore, we get finally that the ratio Pc upon P0, that is E to the power minus 3.188 into 10 to the power minus 3, which I am getting to be 0.997 in 3 significant figures, and that is the numerical answer of the problem. So you can see here there is a very small variation in pressure as you go from the axis to the rim of this cylindrical space station, and that's the end of this problem.
Hello students, you got a glimpse of our video lessons through this small lecture. We have hundreds of lectures like this one covering various topics of advanced school level and intermediate physics in our website. They are exhaustive and often accompanied by elaborate diagrams to make concepts even clearer. They are taught with passion and sometimes with a bit of fun. So, at the end of the lesson, you have a commanding grip on the subject and you are ready for the board and competitive exams. Subscribe at physicsacademyonline.com to access video lectures of highest standard on various topics of physics.